independent, dependent, because you're going to have to know if your denominator changes in between. You have to keep track of all that. And we can tell usually, sometimes they say with replacement, sometimes they say remaining. There's always little words in there that will kind of lead us towards, are they replacing or not replacing, dependent, independent. And we're learning the multiplying rule. The multiplication rule is the and statement. So we talked about the given, and we said this is the probability of B, given that A has occurred. Now, if A is completely independent of B, then this probability will be equal to just the probability of B, because it has no effect on it. If there is an effect, then we have to perform A and then get the result from B. And we can see that in cards. Cards are great for that. You withdraw a card, you hold it. So instead of having 52, you have 51. You have marbles in a jar, 12 marbles. You pull a red, you hold it. Now you have 11 marbles. If you replace it, and they say, put it back, return it to the jar, whatever it is they use to say that, then your probability will not change. So those are the things that we looked at. We started with this, and then we went to this little table. And we said the biggest thing here is finding the given. Because the given is what says probability of B given A has occurred. So we have to make A occur. So we take what's following this, and we say, we did one of these, so let's do the second one. The child has the gene. That's the part we're looking at. If you circle it, when you look for your totals, don't look outside that circle. Look right within that circle. So the probability that the child has a high IQ, given that they have the gene. So we did the gene part. Now we're looking for the high IQ. So here's where you get your probability. 33 out of 72. It's right within that circle. Okay. Can everybody see that? How we did this with the given? This is a dependent probability. Independent probability would say, this is independent. What is the probability that the child has a high IQ? Depends on nothing else but this. There's no other thing that affects this. High IQ, there's 52 in the survey. 52 children have a high IQ out of 102. That's when we're going to use our totals. But if there's a restriction, we're going to use just that little section. Does it make sense to you? Okay, let's see if we can answer these next questions. See if we can answer these. Okay. Probability that the gene is present, given nothing else. So generically, probability that the gene is present. Ignore that circle. 72 out of 102. Good. Total gene is present. 72 out of 102. If you take the totals down here over this grand total, these horizontal lines and the vertical lines have to add up to the same totals. It's just the same data, just accounted for differently. Probability that they have a normal IQ. Good. That's just one event, so it doesn't matter what's happening. Probability of a normal IQ given that the gene is not present. So we go to the gene not present. That's our given. That's our A part that has to have occurred. Now we find what is the probability of a normal IQ. 11 out of 30. Okay? Probability of Oh, I'm sorry, that was a normal IQ, yes. Probability of a high IQ given that the gene is present. So we find this. Go to the green circle. That's all you can stay in is this green circle here that we just drew. Probability of a high IQ, 33 out of 72. See how we work those charts? Okay, when it says probability of B given A has to happen. If A has no effect on B, then it's the probability of B. It's an independent event. If A has an effect on B, we have to perform A, and we will see the difference in B. Okay? These are kind of standard to follow these charts. So now I think we did those, so we don't have to do. I think we did those. Oh no, as a matter of fact, do B. And the probability that the child does not have a gene given that the child has a normal IQ. Use your chart. Probability that the child has the gene, probability, where is it? Probability that the child does not have the gene given that the child has a normal IQ. So probability does not have the gene given that they have a high IQ. A normal IQ? Thank you. Okay, so find me that answer. Take a minute and look at your chart. So Julia, what do you think? Okay, so what part are we looking at first? The given. The normal IQ. So now I'm looking this way. Normal IQ. Don't look out of that blue circle. So the probability that the child does not have the gene, out of 50. Good. Remember, probabilities are part over whole. If your probability ends up greater than 1, that means you took how many times it happened. You didn't take the probability. Okay, so see, we can go that way as well, right? Okay, find the probability that the child does have the gene is present, given a high IQ. The probability that the gene is present, given a high IQ. What do you have, Will?
33
We're going to go for high IQ. We're going to go in this red circle. 52. See it? Go to your given first. Okay. The given tells us that this depends on something else. Something's dependent on this. Okay, and we talked about the two dependencies. If it doesn't have an effect on it, then it's just equal to the probability of the first one. God bless you. If it does have an effect, we have to do this first. Okay, let's decide whether these are independent or dependent. Selecting a king from a standard deck, that's your A. Not replacing it and then selecting a queen from the deck. I want the probability of B given that A has occurred. So A we have to do first. Probability of A is selecting a king, holding it in your hand, not replacing it. B says now select me queen. Independent or dependent? Dependent. What would make this independent? If you put it back. So I am dependent because if I hold the king in my hand, I now have 51 cards to choose from for 4 queens. It made a difference that I held this card. That gave me a dependent event. Tossing a coin and getting a heads, that's my given. A, this is my toss my coin, get a heads. And then rolling a 6-sided die and getting a 6. Is this dependent or independent? Independent. One has no effect on the other. Whether I roll a heads or a tails, what is my probability of getting a 6? 1 out of 6. What is my probability of getting a 6 if I get a tails? Same thing. So regardless of what I toss, my roll is still 1 out of 6. This is an independent event. It's important that you can tell the difference. So you guys take a look at number 3. This has a little subjectivity in here. Which one is going to happen first? Okay, not a great example here, but driving first. This is driving over 85 miles an hour. This is B, getting into a car accident. Is that dependent or independent? Dependent. And it has subjectivity in there. Does it mean that you will get into a car accident? It just means your probability is there because you're over the speed limit, you're driving too fast, blah, blah, blah. So there's a lot in there to add. Just has a little subjectivity in it. Okay, I want you to take a minute, and I want everybody to do these 2. That has to happen first. This is my smoke my pack, smoking my pack every day. B is developing a chronic lung disease. Dependent or independent? Dependent. This is subjective. Does it mean that something else can't cause that? They're just saying they're always advertising smoking causes lung cancer. So if you're going to smoke, if you're going to be likely to get lung cancer. Tossing a coin and getting a heads, that's here, I get the heads. And then tossing the coin again and getting a tails. Independent or dependent? Independent. Coin tosses are independent of each other. Their probability is always the same. In fact, you're going to see that your probability of getting 3 tails, getting 3 heads, getting 2 tails and a head, they're all the same because probability is always 1/2. Sometimes on probability problems, they'll weight the coin because 1/2, 1/2, you really can't tell which one you're looking at. So they'll usually weight the coin so you can see your probability change. Not a fair coin, obviously, but a weighted coin. Okay, so now we get to multiply. For dependent events, if you have a probability and you have an AND condition, we're going to multiply. For both of these cases, we multiply. The only difference is, if you have an independent event, first you have to figure out that probability based on its dependency. So we're still going to take the 2 situations and multiply them. You'll kind of see it. You'll never go back to looking at this, but you'll know which one you have to multiply. So 2 cards are selected without replacing the first cards. Without replacement, is this dependent or independent? Independent. Sorry, dependent, right? Dependent. Okay. 2 cards selected. One we keep, then we would take another one. Find the probability of selecting a king and then selecting a queen, given that you selected the king. Okay, so now I've got a dependent event. So what's the probability that I get a king and then a queen? My queen has this condition. My king is fine. So what's the probability of selecting a king? 4 out of 52. Okay, and says I'm going to multiply. Now this one has a dependency. What's the probability of getting a queen given the fact that I'm holding that king? 4 out of 51. And you're going to multiply. We don't need to worry about this. I just need you to know that if it's independent, it affects your probability. If it's dependent, it affects your probability. If it's independent, it does not affect your probability. Now, multiply across. Make life easy. Do it on your calculator. If you do it on your calculator, it gives you a decimal. That's fine. I think this is 2652. 2652. Okay. Now, I kind of like looking at decimals just because even when you reduce them, if your numbers reduce to two different denominators, you're going to have a very difficult time comparing them anyway. If you want to leave them with a common denominator until the very end, you can do that, or you can keep 3 decimals. And I think the 3 decimals show you the rarity, because even if you move the decimal point, it's less than 1%. I mean, yes, this looks small, 16 over 2652, but I think this appears to us like a little bit, I like the decimal. You know, I don't know what you prefer, but you'll figure that out. Okay, let's try another one. A coin is tossed and a die is rolled. Find the probability of getting a heads and then rolling a 6. I want to get a 6 and a heads. Okay, are they, I want to get a heads and then a 6. It doesn't matter which order you do them in because it's going to be the same thing. But this guy, if it's independent or dependent, we have to worry about on the heads. Is there a dependency or an independent here? Does a coin affect my rolling of my die at all? No. So what's the probability that I get a heads? 1/2. What's the probability that I roll a 6? And I multiply. 1 out of 12. My chance is 1 out of 12 of getting this combination. Okay. All right, you guys try this one. Everybody pick your head up, try it. My probability should be a little bit more fun here. It gets harder. It gets harder. We obviously have to start easy, but it's going to get harder. So try the first one. This is your sentence, successfully swimming through that Columbia River Dam. If you go to a decimal, it's probably the easiest. I want 3 places on your decimal. I like a decimal. If you want to give it a fraction, make sure you do it in reduced, for your final answer is reduced fraction. So, see, my problem is this. Well, this is a decimal anyway, so you would give it in a decimal. Like, even when you do the cards, if you're looking at 52, you kind of get a perspective on, my deck is 52 cards. I know, like, I have a chance of 4 out of 52. Once you start multiplying your denominators, like if we do it times 51, you kind of lose track of, what was I have 2 decks now, or did I do this twice, or where did this big number come from? So I think the decimal probably gives you a better feeling on your probability. If you can see it, like when we do the adds, and you leave the same denominator, it makes more sense. But the multiply, I think the decimals make a little bit more sense. So we want the probability that one salmon swims through and another salmon swims through. Is this independent or dependent? Independent. One salmon getting through has nothing to do with the next one getting through. unless the first one scared the second one and the second one doesn't want to try it. But technically they're independent. Independent means my probability will not change. Chances are if they give you a decimal, your probability will not change. Because how do you take that away? How do you take one away? It's hard. So the probability that one successful salmon gets through and another salmon gets through, and you're just going to multiply these guys. And if you multiply them, and the number should be a good sized number. Okay? So the probability is a little stronger that two of them will be successful because you have a good success rate for one to happen. If your success rate was small, say my probability of getting through was 0.10, and you had to multiply two of these. Okay? 0.01 now, it's going to be very, very small that your probability of two of them to get through would happen. But if it's bigger, it's easier to understand that one. Okay, two cards are selected from a standard deck without replacement. Independent or dependent? So it depends what I get the first time for what I'm doing the second time. Find the probability that they are both hearts. The probability of one heart and another heart. So first time around, what's the probability of a heart? 1/4 or 13 out of 52. Second time around, what's the probability of a heart? Good, 12 out of 51. I now have 51 cards left. I now have 12 hearts left. Okay, and multiply those guys together. See, once you start multiplying your denominators, you kind of lose track of the problem. So I think it's easier to look at in a decimal. So a little bit more than 5, almost 6% of the time. So you have a 6% chance of that happening. Everybody good so far? Okay, for all you sports people, they redid a lot of these problems in here. And they made it, I guess, a little bit more for you guys. They had successful surgeries. They made this one an ACL reconstructive surgery. So for an ACL reconstructive surgery, the probability that the surgery is successful is 0.95. Okay, find the probability that 3 ACL surgeries will be successful. So what do you think I did? Just multiply. Good. I want the probability of one success, and another success, and another success. I just subscripted, so you're going to multiply. And that number should be a pretty good size number because the success rate is good. Because who would want to do the surgery if the success rate was poor? You certainly better not go to that doctor. Okay, so if you multiply them all together, you get about 86% probability that all 3 will be successful. That's a nice probability that all 3 will be successful. Okay, so do you see what the multiply is doing? The and statement causes us to multiply. The or we'll concentrate on in the next, the 3.3. They don't like to mix them because the or is the adding one. And it always has a little bit extra little problem in it. But the multiply is the nice one. It's straightforward. Find the probability that none of the 3 ACL surgeries were successful. How would I do that? If the probability of success is 0.95, what is the probability of not successful? Point what? 0.05. So now I want 3 of these guys. Okay, I want 3 of these when I'm going to multiply. Most important, your and statement says multiply. So your calculator, put it in your calculator for me and tell me what you get. Read me what it says. It says 1.25. That's not possible for our probability to be over 1, right? So what's the rest of it, Jared?
E
E negative 4. I want everybody to look up here because if you give me 1.25, it is wrong. It's a scientific notation number where my exponent is a negative 4. You can't possibly have a probability greater than 1. And multiplying that tiny little probability could not even give you close to a 1. So this e to the negative 4 says the exponent on your scientific notation number has to be moved, the decimal has to be moved 4 places to the left. I certainly wouldn't want to move it to the right. That'd be really, really a very high number. So I'm going to move it 4 times.
Honestly offensive. We know what scientific notation is. Like, we all took chemistry or AP, whatever. It's like my 5th time learning this.
And I get it, but not all of my kids in here will get it. Because they're not used to looking at the calculator. Okay. All right. So, let's keep in mind what we had. And let's say that the probability that at least one of these 3 surgeries is successful. If at least one is successful, what is the case that I don't want? I can have at least 1 successful. Can I have 2 successful?
Yeah.
Yes. Can I have 3 successful?
Yes.
Because it has to be at least 1. So what's the only case that I don't want?
Just one.
No, I want 1.
Oh, no.
I don't want none. So can I use the complement? 1 minus none. Can I use the complement here? This is my complement. So 1 minus 0.000125. And that's going to be a very large number. So about 99875. 999. Okay, very, very high number. I want at least 1 successful. It leaves me 3 possibilities. 1 successful, 2 successful, or 3. The only one I don't want is the none. Now, if you remember doing these in Algebra 2, okay, so the probability that 3 rotator surgeries are successful. So, Will, how'd you solve this one?
0.9 times 0.9.
Okay, and what'd you get?
7.7.
0.729?
7.29.
29? Okay. I just didn't hear you. Okay, 0.729. So you have about a 73 chance of probability that all 3 will be successful. Okay, find the probability that none of the surgeries are successful. So if the probability of successful is 0.90, what is the probability of not being successful? 0.10. So 0.10, and our and statement says multiply. So what do we get?
Can we just cube it?
Yeah, absolutely, you can cube it, Michael. What'd you get?
It's not. It's 0.001.
Or you can give it to me. Give it to me in a scientific notation number.
It's 1 to the. Now I gotta do it. Move over thing. -2,
Michael.
It's 3.
Oh, it's not 3. It's negative 3. It's negative 3. If it's a positive 3, you're getting a very large number. So not everybody is very comfortable with our scientific notation numbers. Okay, find the probability that at least 1 out of the 3 are successful. Then I can have 1, I can have 2, or I can have 3. The only one I can't have is the none. This is your complement. So 1 minus 0.001, a 0.999 probability, almost 100%. Because our chances were very, very low there. Everybody good with this? Okay. All right, and the last step is they just like kind of put these things to probabilities. Yeah, this is like a huge explanation here. Now, guys, just listen for a second.